instructor for this course, Professor Curtis, and this is the lecture video for Chapter 5, Newton's third law of motion. Let's get started. So, it may be last in line of Newton's three laws of motion, but Newton's third law of motion is certainly not the least of them. And here it is. For every action, there is an equal and opposite reaction. So this is actually kind of popularized throughout society. Everybody seems to know about this. They may not be able to recognize it as Newton's third law of motion, but they know the words. For every action, there's an equal and opposite reaction. But think for a moment of what this really means. This means that you can't have a force acting by itself. There's always going to be forces existing in pairs, because for every action that you would have, there's an equal and opposite reaction. There must be an opposition to everything that we have in the world. And that's the way the world is designed. Think about it. Look at the examples that we have here. For an automobile, you got the tire pushing on the road, so then the reaction will be that the road pushes back on the tire. Gas expelling out the end of a rocket, the rocket's going to push the gas out of the rocket, and in exchange, the gas pushes back on the rocket, propelling it forward. A man pulling on a spring, it elicits the reaction of the spring pulling back on the man. So every time you have a force, there's always going to be an opposing force that's reactionary to the force that you have. So when we're calculating the net force on the object, we want to make sure we have all the right forces in our calculation. And this is where Newton's third law comes in very handy. It helps us to find all the right forces in our calculation. But to do that, we need to first define a system. What that means is that we're simply going to take an area of interest that we want to study. So if we're looking at the eclipse here, let's define our system, say, as the sun and moon together. That's going to be our system. Okay, so everything outside the system will then be the surroundings. And everything that we have, with the system and the surroundings, that's going to be what we call the universe. Now, it's pretty simple way to look at things. We define a system. We can define that system however we want. Does not matter how we define the system. And that's actually very useful, because sometimes defining the system a certain way helps us find a solution much more easily to certain problems. But however we define the system, the laws of physics are going to hold true. So we have a system we define. Everything outside the system is called the surroundings. And then the universe is just the sum total of everything, system plus surroundings. The way we define the system is important, because the only forces that we're going to consider in our net force calculation are the ones that cross a system boundary. So in the example that you see here on the screen, we've got an apple and an orange. The apple there's a rope there tugging on the orange. And so, we're going to include the tension in that rope in our net force calculation, because it crosses a system boundary. We're defining the system as including only the orange. However, if we change the system boundary to include the apple now, the tension in the rope no longer crosses a system boundary. It's entirely internal. And because it does not cross a system boundary, we do not include it in our net force calculation. So the only forces we want to consider when calculating the net force on an object are the ones that cross a system boundary. Because every object with mass has weight, Newton's third law of motion says that there's going to be a reactionary force to the weight that the object has. And these two forces in particular are the action-reaction pair that Newton's third law says must exist. So the first force that we have on an object, obviously its weight. Gravity is going to pull on that object, push it closer to the ground. And the ground is therefore going to have a reaction to push back against the force of that weight in an equal and opposite magnitude and direction. So this support force is going to act perpendicular to the ground. It always acts perpendicular to the ground. And because of that property, this support force that's reacting to the force of gravity, the weight of the object, is what we call the normal force. And that's because normal is another mathematical word that means perpendicular. We often represent this normal force with a capital letter N, and here's where you gotta try not to get too confused, because yes, we use that capital letter N to represent the units of force in the SI system, which are newtons. So N could represent a particular force, the normal force, or it could represent the units of force in general, which are newtons. Try not to get confused. I know some students, it's very easy for them. Just try not to get confused with this. The normal force has a very special relationship with the friction force. They are directly proportional to one another. And here's the relationship in mathematical terms. We're representing the friction force with that lowercase letter f. And then we've got this funky looking u, which is really a Greek letter called mu. That's right. It's like think about a cow with a speech impediment. Instead of saying moo, you say mew. Mew. So or maybe it's like a mutated hybrid of a cow and a cat. Instead of saying moo or meow, it says mew. Anyway, moo. Now I'm getting mutated with my tongue. Mu. And then we've got the capital letter N, which of course we just learned represents the normal force. So this mu is a proportionality constant. You can think of it as the amount of friction that exists between two surfaces that are moving against each other. Remember, there's two types of friction though. There's static friction and kinetic friction. So of course there's two coefficients of friction. There's a coefficient of static friction and a coefficient of kinetic friction. That's why we use the subscripts, the S and the K, so we know which one we're talking about. Regardless of which coefficient you're talking about, they each have values that can be anywhere between 0 and 1. And the kinetic friction coefficient is always going to be less than the static coefficient of friction. So if you're given two coefficients and you're wondering which is which, the static coefficient of friction is always going to be greater than the kinetic one. Always. Let's look at an example problem to illustrate how all this plays together. Imagine we have a 50 Newton box at rest on the floor, and we have a coefficient of static friction of 0.35 and a coefficient of kinetic friction of 0.28. What force do we need to exert on the box in order to start it sliding on the floor? Okay, well, first, let's define our system as just the box. So we're going to look at our system as just the box. So anything that crosses over that system boundary is going to be included in our calculation. Second, identify all the forces that cross those system boundaries. If it doesn't cross the system boundary, we're going to ignore it. So first, we want to look at this. Say, okay, well, obviously the box has weight to it, the force of gravity acting on the box. And we've got that from the problem, 50 newtons. And then we've got a normal force that's acting in reaction to that weight. That's Newton's third law of motion. We're going to push against the box with a certain force, and we'll just call that force F. And then friction, of course, is going to resist our motion to the box. And so we'll represent that with a lowercase letter f. Keep in mind that the friction we're looking at is static friction because the box is at rest. So when you're just pushing on the box to get it to start moving, you're dealing with the coefficient of static friction. This box is at rest. okay, which means that we have equilibrium in all directions. And when you have equilibrium, the sum of the forces in that direction is going to be 0. We have equilibrium in all directions, so the sum of the forces along each direction is going to be 0. So let's look at the vertical first. In the vertical direction, we have the weight going down and the normal force coming up. The weight, we know from the problem statement, is 50 newtons. That means that in order for this to balance out, the normal force must also be 50 newtons. Then looking along the horizontal direction, we've got the force that we're using to push the box, and that has to be equal to the friction force in order for everything to balance out. Well, the friction force is the coefficient of static friction, 0.35 from the problem statement, times the normal force, which we just saw was 50 newtons. So you multiply that together and you get 17.5 newtons. So this 17.5 newtons is the maximum force you could push against the box without it moving. If you go greater than 17.5 newtons, so if you go to say to 18 newtons, then the box will start to move. 17.6 newtons will do the trick. 17.5 is the maximum that you can push against the box without it moving. Once you exceed that, now you've exceeded the force of the friction, that's the static friction, and now you start getting into the realm of kinetic friction, which of course is always going to be less than the static friction. So now you go ahead and try an example of your own. Here we've got the same 50 Newton box under the same conditions. So we've got the same coefficients of friction, but now the box is moving. It's sliding to the right with constant velocity. What force must you apply to the box to keep it moving at constant velocity? So go ahead, stop the video here, try this problem out in your workbook, and then when you get done, come back and we'll see how well you did. Okay, let's see how well you did with this. So we've got the box, and we're going to define our system as just the box. And now we're going to look at all the forces that are crossing system boundaries. So first up, we've got the weight of the box, gravity pulling down on the box. There's going to be a reaction to that weight. Newton's third law of motion says there's a reaction force, and that is the normal force pushing back up against the box. We've got the force that we're pushing on the box to move it to the right. And then, of course, friction is going to resist that motion that we give to the box. So these are the forces that we have on our box. So now we go and we try to figure out, okay, what's the value of all these forces? What's the magnitude of each of these forces? We have the direction. Now we need to figure out the magnitude. Well, the weight from the problem statement was 50 newtons. So in order to balance out in the vertical direction, the normal force must also be 50 newtons. Then along the horizontal direction, we can look at the friction force and say, yes, the friction force is equal to the coefficient of kinetic friction, because the box is moving, times the normal force. So 0.28 times the 50 newtons gives us 14 newtons. So in order to balance out, the push force that we're exerting against the box must also be 14 newtons. This is the minimum force that we need to apply to the box in order to keep it moving. If we apply a greater force than 14 newtons, the box will actually accelerate. It will actually pick up speed. And remember in the problem statement, we want to keep it at constant velocity. So we have to keep that force at 14 newtons. As long as we keep it at 14 newtons, we will continue to move the box towards the right. Now, if we go below 14 newtons, then the friction force is going to be greater than our push force, and it will begin to slow down. And if we don't pick the force back up to 14 newtons, then eventually the box will come to rest, and we're going to have to put in even more force. Because remember what we saw before, that the force to get it to start moving was 17.5 newtons. So it costs us more to get the box to move at the start than it does to keep it moving. And this is the way the natural world has been constructed. It takes more to get something to go than it does to keep it going. We see this not only in physics, but also in chemistry. Many chemical reactions have an energy requirement. So you need to keep supplying energy to the reaction in order to keep it going. But the energy that you need to start the reaction, called activation energy, is much greater. So oftentimes you have to put in more energy to get the reaction started than you do to actually maintain the reaction. It's the same thing in life. Have you ever noticed how it's harder to start doing something than it is to keep doing it? I mean, it's harder to get off the couch and start getting to work. But once you start getting to work, you find your groove and you can just keep going and going with it. But it's so much harder to get it started, to get ourselves to start to do something. That's a reflection of what we see here in the natural world. It's much harder to start something out than it is to keep it going. That brings us to the end of this lecture video. I hope you found it helpful. Thanks for watching, and we will see you in the next video.